Now, thank you. And thank you for the invitation. I'm happy to also contribute something to the birthday workshop of the GKP code. And I will be talking about Surface-GKP codes with design bias. And this is based on a work together with Robert König and Margret Heinze, also here from Munich. And I will first give you an introduction telling you what it all is about, and then we will have to go through some preliminary information, mainly about notation, conventions, and assumptions concerning GKP and surface codes. And then we will be ready for the main idea of our work, which results in modified Surface-GKP codes. And finally, I will present you our numerical findings about the error thresholds for these codes. Okay, so the Surface-GKP code is basically just the concatenation of the birthday code with a surface code. So the physical qubits of the surface code are logical GKP encoded qubits. And these codes were considered before, for example, by Fukui and co-authors, Woyo and co-authors, and No and Chamberlain. And it was found that the noise resilience of the surface code can be improved by combining it with a GKP code. And actually, one can even make this improvement bigger by, for example, also considering the GKP syndrome information in the surface code decoding step. Now, another thing that the surface code can also benefit from is bias noise, or a certain kind of bias noise. And more concretely, I mean here, if we consider IID Pauli noise on every physical qubit, then it may happen that one Pauli error is more likely to happen than other Pauli errors. And in such situations, works by Tuckett and co-authors showed that sometimes we can use this noise bias and improve the error threshold. So now, the idea of our work is actually rather simple, namely, we want to make use of the resilience of the surface code to bias noise by modifying the Surface-GKP code. And more precisely, in the before mentioned works about the Surface-GKP code, the base GKP code that was used was a standard GKP code, which is symmetric in the position and the momentum operator. But if we, on the one hand, now use an asymmetric version instead, and on the other hand, adapt the concatenation procedure appropriately, then we will see that we will end up with a bias noise at the level of the surface code, and our numerics indicate that we indeed get an improved threshold with this strategy. Okay. So some preliminaries. First, some notation. We denote by Q and P the position and the momentum operator, and we gather them in a vector R. And then the commutation relations can be written in terms of the matrix J, which is defined below here, and is associated with the given symplectic form. And then the displacement operator can also be written in terms of this matrix J. And this operator translates by conjugation the vector of mode operators R by the amount psi in phase space. And the commutation relations of two such displacement operators can be written as given in terms of the symplectic inner product. And this means that the two operators commute whenever the symplectic inner product of their vectors, namely psi and zeta, is an integer multiple of 2 pi. Yeah. So now, a symplectically integral lattice is a lattice in R2, which is generated by vectors whose symplectic inner product is equal to plus minus 4 pi. And now, the GKP code space is stabilized by the lattice displacements. And one can check that the stabilizers actually commute by using the integrality condition. And now the symplectically dual of the lattice L is generated by the vectors xi per, which satisfy the given relations with the lattice generating vectors xi's. And if you now recall that the condition for two displacements to commute was that the symplectic inner product of their vectors is an integer multiple of pi, and we see that this condition actually means that the dual lattice displacements commute with the displacements of the lattice itself. In other words, they are in the centralizer of the stabilizer. So now the elements of the centralizer are logical or logical operators in the sense that they leave the code space invariant, but they may or may not act non-trivially on it. And two elements of the centralizer have the same logical action if they differ by multiplication by a stabilizer, or in other words, if the difference of their corresponding vectors lies in the lattice L. And this means that we get a complete family of inequivalent logical operators indexed by the set L per modulo L of cosets of L. Okay, so I know this was a bit dry, and to compensate that, we will now have a look at examples and pictures. So the first example is, of course, the standard symmetric GKP code, which corresponds to a square lattice of spacing 2 times square root of pi. And this is marked with black dashed lines in the picture. And the dual lattice is just half of the spacing and is marked with blue lines in the picture. And the logical operators are generated by the displacements by one side in one of the directions of the dual lattice. And these generating logical operators can be identified with logical Pauli operators. And one thing to mention here is that this identification with the Pauli operators is not unique, because periodic permutations of x, y, z would also be valid, because these preserve the commutation relations among the operators. Okay, so now the last thing, which is also marked on the picture, is the Voronoi cell of the dual lattice. This is this blue rectangular around the origin, and this is just the set of points which are closer to the origin than to any other point of the dual lattice. And this will be relevant for the decoding strategy that we use. Okay. Good. So now another example is the GKP code corresponding to a rectangular lattice. And here again, the lattice itself is marked with dashed black lines, the dual lattice with blue lines, and the Voronoi cell of the dual lattice is this blue rectangular around the origin. And here, the parameter R is the ratio of the generating vectors of the lattice. And in the picture, R is equal to 4. And in the example that we have seen before of the square lattice, R was, of course, equal to 1. And now, so one thing I would like to mention here is that one can get the rectangular lattice by applying a symplectic matrix SR, given here, to the square lattice. And this is actually a more general concept, namely symplectic transformations leave the integrality condition of the lattice invariant. And this means, this is just by definition of a symplectic matrix. And this means that whenever we apply a symplectic transformation, we actually end up with another GKP code. And one can actually even show that we can get all symplectically integral lattices by starting with the square lattice and then just applying symplectic transformations. And on the level of code spaces, symplectic lattice transformations are just the application of a Gaussian uniter. So the noise channel that we consider is, I think, the standard noise channel for GKP codes, namely displacement noise. which was one special case of what Jonathan presented, I think. And here the function f is a probability density function associated with some random variable set. And we are specifically interested in the case where set is described by a centered normal distribution, which means that f is of the given form, where sigma is a covariance matrix, and this kind of noise is also called Gaussian displacement noise. And usually, to assess the noise resilience of GKP codes, one considers the isotropic case, where the covariance matrix is proportional to the identity, and then one varies the parameter sigma, or small sigma, which is just the standard deviation. Okay. So now, error recovery, or the error recovery we consider here, proceeds as usual by first measuring the syndrome and then applying a unitary correction operation according to the syndrome. And the syndrome one gets by measuring the stabilizers, or the stabilizer generators, which are, as we recall, the displacements with respect to the lattice generating vectors. So now, since the symplectic inner product of these vectors with those, or the generating vectors of the dual lattice, is exactly 2 pi, this means that the operators Q and P are measured modulo the dual lattice. So we get a syndrome in the Voronoi cell of the dual lattice. And here we have again these Voronoi cells marked with blue rectangulars for our 2 examples of R equals 1 and R equals 4. So now we choose the specifically simple strategy of nearest lattice point recovery, which means that we basically just undo the error that we see. That is, we shift back according to the syndrome vector. And this is not maximum likelihood decoding, at least for a general error distribution, but it is expected to work pretty well for distributions which are concentrated around the region, so mainly small displacements. And because of its simplicity, it's commonly used in when one works with GKP codes. Okay, now I have another figure showing the phase space regions corresponding to displacements, which correspond to errors that we recover successfully from with our strategy, namely the white regions, and all other displacements, or for all other displacements, we end up with a logical error with our recovery procedure. Okay. So that was it to GKP codes. I won't go into too much details for the surface code, I promise. So we consider L times L surface codes with smooth top-bottom boundaries and rough left-right boundaries, and the qubits are, as usual, placed on the edges of the grid, and the stabilizers, which are marked with black lines in the picture, are on the one hand the vertex stabilizers, which are poly X operators acting on the qubits on the edges incident to the same vertex. And on the other hand, the plaquette operators or stabilizers, which are poly Z operators acting on the qubits on the edges surrounding one cell or plaquette of the grid. And now the logical operators, the logical poly X and poly Z operators are the string of corresponding operators acting along the right and the top boundary respectively. So for an L times L surface code, we have one qubit encoded into n equals L squared plus L minus 1 squared physical qubits. And since the logical operators have minimum weight, the codistance is equal to their weight, which is just L. So the noise model that we consider here is IID Pauli noise on every qubit. So the noise channel is a tensor product of Pauli noise channels with respect to the probability distribution P for every physical qubit. And now for the error recovery, since the surface code is a stabilizer code, we can proceed here as before for the GKP code by first measuring the syndrome and then applying a unitary correction operation according to the syndrome. And the best strategy for this recovery would of course be to choose the maximum likelihood decoder. But as we know, finding the most likely coset is not trivial, even for simple IID noise models. And this means that the maximum likelihood decoder cannot be realized efficiently. And to overcome this obstacle, Bravi, Sukhara, and Vargo proposed a decoding strategy which approximates the maximum likelihood decoder. And this strategy depends on some parameter chi, the bond dimension, and it becomes exact, meaning the maximum likelihood decoder itself for chi going to infinity. But in contrast to the maximum likelihood decoder itself, it is efficiently computable. And I won't go into more detail about that here, but this is the decoder that we consider for the surface code. Okay, good. So now, to tap into the potential of the surface code to correct biased errors, we make the following modifications of the typical square lattice Surface-GKP code. Namely, firstly, we apply a Gaussian unitary to each mode, which corresponds to performing a symplectic transformation of the lattice, and which yields the modified GKP code states given here. And in particular, it maps isotropic Gaussian noise on the level of modes to biased noise on the GKP qubit level. And the second thing that we change is we change the way the GKP code is concatenated with the surface code. And namely, we map Pauli Y eigenstates instead of Pauli Z eigenstates of a GKP qubit to the modified GKP basis states. And this ensures the given identification of qubit operators with logical GKP operators. And this whole second part is actually just a periodic permutation of the Pauli operators, which you are free to perform, as I mentioned before. Okay, so now for a rectangular lattice GKP code, this leads to an effective noise channel which is independent, which has independent Y and Z noise. And more explicitly, these expressions QZ and QY can be computed to be of the following form, where ERF is the error function given below, sigma is the standard deviation of the Gaussian displacement noise, and R is the ratio. And you don't have to study these expressions in too much detail. What is important is that the first expression is monotonically increasing in R, whereas the second expression is monotonically decreasing in R. And this in particular means that we get that Pz is much smaller than Py for R large enough. So in other words, by tuning the asymmetry ratio, we achieve the desired bias on the level of the surface. Okay.
So
but,
Lisa, you have 5 minutes.
I have 5 minutes. Yes. Thanks. So, however, even though we also have dominant Pauli Y noise, this is not exactly the same a noise model as they considered in the works of Tackett and co-authors that I quoted in the beginning. So we had to do our own numerics, and this leads me to our numerical results, namely our main numerical findings can be summarized in the following plot, which shows the threshold estimates we found for different asymmetry ratios in a modified rectangular Surface-GKP code. And the threshold, we mean here the critical noise strength sigma, below which we can make the logical error probability arbitrarily small by taking the distance of the surface code large enough. And on the horizontal axis, you see the different asymmetry ratios R. On the left vertical axis, you see the estimated threshold values of the standard deviation of the Gaussian noise. And the right vertical axis is actually just for comparison. It shows the probability Qx of a poly X error corresponding to the same standard deviation. So if we have no modification, like if you would work with a standard Surface-GKP code. Okay, so what we see in this plot is, on the one hand, for R equals 1, so in the symmetric case, we get a value of 0.54, which is about what they also get in the work by Wu et al., which actually wouldn't have to be the case because, as I said, we have a different concatenation procedure. But what you also see is that for R equals 3, we get a value of 0.581, which is clearly bigger than the value at R equals 1. So this plot indicates that we actually do get an improved error threshold with our strategy. So another thing to mention here, maybe obviously this improvement is not monotonic in our numerical results, but we think that it's quite possible that this is just an artifact of the limited code sizes that we were able to simulate. Okay, so with that, I already get to possible future directions. So so far, we did not explore all the possible choices of codes and decoding strategies in our simulations. And one possible additional optimization will be over axial lattice angles, which could actually yield another benefit because, for example, it was already mentioned in the Surface-GKP paper that if one chooses hexagonal lattice GKP codes instead of square lattice GKP codes, then one gets better error correction properties because of the difference in volume of the corresponding Voronoi cells. Another thing that one could do is to use the GKP syndrome information in the surface code decoding step. And in the symmetric case, so for R equals 1, it was actually shown in several works that this can significantly improve the threshold. So other possibilities would be, for example, to establish the monotonicity of the logical error probability as a function of the degree of asymmetry, then studying the effect of non-ideal or finite discrete GKP states, as well as noise in the syndrome information and so on. So for the first 2 points, we actually did some numerical tests, which indicate that these additional optimizations do not negatively interfere with the use of asymmetry. Okay, good. So let me conclude. Firstly, our numerical results for the modified Surface-GKP code indicate that a suitably chosen Gaussian CV-into-CV encoding leads to a deformation of the effective error, and on the level of the GKP qubits, which known decoders for the surface code can benefit from. And actually expect that similar strategies could also yield a benefit for other CV codes that are getting that one gets by concatenation. And in particular, our results also show that no-go results for Gaussian CV-into-CV encodings, saying that encoding bosonic modes into other bosonic modes by means of a Gaussian unitary cannot be beneficial, no longer applies when considering concatenated codes. So with this, I'm at the end of my talk, and I thank you very much for your attention.
Thank you, Lisa. So we have one question for now, and I have also another question myself. So is there an intuition for the optimal bias ratio of around 3? Okay. So you
The optimal ratio?
So the R that you show in the curve, you have this, I guess you mentioned that this might be just a numerical artifact, but here you see an R which is equal to 3, which is the optimal. Do you have any intuition about this? Why there is this optimal value of 3?
Yeah, actually, I mean that I said that we think this is an artifact of the limited code sizes. We actually did some, like we have different simulations showing that we actually get the expected behavior of the for the different ratios as soon as we have bigger code distances. We have a more consequent behavior, like as we would expect it for the graphs that we get. Whereas for small code sizes, for higher ratios, somehow the lines of the logical error probabilities get messed up at some point. So I think this might more be like the ratio 3 might more depend on the code sizes that we actually chose. That it would actually be higher if you had simulated higher, like chosen even to start at higher code sizes, which is difficult because already like that the simulations took pretty long. So I don't think the R83 is a special point. I really think it's about what code size.
So there is a follow-up comment by I don't know, I think it's Anna maybe. It says that I didn't catch that, thanks, but I suppose there must be an optimal finite R even for D which goes to infinity. So I don't know whether you have any comments on that. Do you think there is going to be a optimal finite R if we forget about this artifact? So
well, I think it would not you wouldn't get at some point you would not get any further improvement, like that you would get a finite R which after which you just stay on the same level. But I cannot make a definite I cannot give a definite answer to that because I think these are just simulations, not rigorous mathematical proofs of some statements. So I can just say what we saw in our simulation.
Thank you. So we're going to follow up with another question. How do you do the encoding with symplectic operations that you mentioned at the end? So
you mean
I'm not sure. So it's a question from Julia Farini.
Yes, so. Maybe I can help. Yeah, just at the end, it was at the conclusion that you mentioned some no-go theorem that do not apply here. You mentioned that in principle, it's not to encode in GKP states with symplectic operation, but then you said something that here this doesn't apply, and I didn't understand why.
So the thing is, these no-go theorems tell us that, which still applies here, that if we use Gaussian encodings, then we can maybe make the noise in one quadrature smaller, but not in both. But it wouldn't like go up in the other. Like you can see this with the standard deviations. If you divide it by some if you can divide the noise, the deviation in one quadrature by some amount, then you have to multiply the standard deviation of the other quadrature with the same amount. Like the smaller you make it in one direction, the bigger you make it in the other direction. Like you can just squeeze it, but if you squeeze it in one direction, then it will become broader in the other direction. So this is still true. The thing is just these theorems somehow you tend to think that okay, then Gaussian encodings won't help in any case. Like it's not useful. But actually, in our case, it is useful because with this additional concatenation with the surface code, we don't care that in one direction it gets worse, but we just use this asymmetry of the noise in order to get a better decoding strategy.
Okay, it's very clear. Thanks. Thank you.
So yeah, I guess Julia, you had another question, but it's more for Ulrich, I think. Yeah. So right, is it more for Ulrich? So I guess the question was, how can we use an optical GKP to generate a Surface-GKP? So I guess maybe Ulrich can respond to it in the Slack or something. It's maybe better. I don't know.
Yeah, Lisa had some references in the beginning. I was wondering if in the references that she had, there were also tips on how to generate the Surface-GKP once you have the GKP optically, for instance. Yeah, but yes, I would be grateful if either Lisa or Ulrich would reply to this, either in Slack or through any channel.
Okay. So I guess if there is no comments from the organizing committee, we could maybe start